everybody, we are back with lesson 5. I kind of split up this lesson into two parts because the last episode we talked about reactions and I wasn't quite sure where to go from there because I felt like we hadn't gone into enough detail with them. So lesson 5a and 5b are going to be centered around different types of reactions and working with them. I thought it best to start off with theoretical, actual, and percent yields because those will help us in our 5b lesson, which is about combustion reactions and empirical formulas. So we are going to jump right in with some definitions. It's important to know what theoretical yield is, and that is the maximum possible in a reaction, the maximum amount of product formed in a reaction. This is most likely going to be just a calculated value because your theoretical yield will never equal your actual yield, which is the experimental amount of product formed. So one's on paper and one's in real life sort of thing. The reason that you don't have matching numbers between theoretical and actual yield is because when the experiment or reaction is performed, some of that energy and matter is going to get lost to the universe as a byproduct. So we're never going to have a fully complete reaction. There's always probably going to be a percent, unless you're in a really controlled environment, and even then I can't even say. Anyway, so we can kind of see how these yields relate to each other and see how efficient our process is when we look at the percent yield, which is, you know, kind of like calculating your grade, you know, except in this case it's with product. So your actual yield would be your experimental amount over your theoretical yield, so perhaps it's the points you scored on something out of the points possible, and then you multiply that by a percent. And from there you can find the efficiency of a reaction, and you can see how efficient your process is, or perhaps something's getting in the way, a confounding variable that you haven't found yet, and this might be a way for you to find that. So these are pretty important. You're going to get asked about them a lot on tests and all that. Professors love to do that. We're going to move on to limiting reactants. And those are the reactants with the least presence or the smallest moles. So they're the least volume, not volume, but mass sort of thing. I'll explain. It's kind of hard for me to put into words, but hopefully visually it makes sense. So if we just have this generic equation, 2a plus 3b plus 5c yields a3, b3, c5, can we tell what the limiting reactant might be in this equation? Well, we can, because it's a pretty simplified equation and it already gives us the molar ratios as it is. We start out with 2 moles of A, but we need 3 moles of A. We start out with 3 moles of B, and we have 3 moles of B. And we need 5 moles of C, and we have 5 moles of C for this final product. So it's intuitive to say that the 2A is the limiting reactant. They're not always going to be this straightforward, but this is kind of a generic way to start looking at it. If you struggle with that concept, I know I did for a while with limiting reactants, you can think of it kind of like a recipe or something like that. I don't know about you guys, but I love pizza. And if, say we want to make a full pizza, and we have, well, sorry, excuse me. Say we want to make a full pizza, we're going to need 1 dough ball, 2 bags of cheese, and 1 can of tomato sauce for a regular cheese pizza. That makes 1 cheese pizza. But say, experimentally, we have 3 dough balls, 3 bags of cheese, and 3 cans of tomatoes. So what do you think our limiting reactant is? Well, and how many pizzas can we make? Kind of like how many moles of product can we make? We have enough dough balls because we only need 1. We have enough cans of tomatoes because we only need 1 and we have 3. And we have enough bags of cheese because we have 3. But you can make 3 pizzas with 3 dough balls, and you can make 3 pizzas with 3 cans of tomatoes, but you cannot make 3 pizzas with only 3 bags of cheese. You would need 6. It's kind of the same idea. You can apply this to molar ratios in reactions, and it works the same way. Hopefully that makes sense to you guys. Some people like to do sandwiches. I prefer pizza, but that's just me. Okay, hopefully you got that down. I'm gonna move on. we're going to go on to kind of what it looks like, what finding a limiting reactant and looks like on paper, perhaps in class. So we're given this equation, and we're supposed to find the limiting reactant. It's kind of hard to find out where to start, right? Well, the big thing is to balance the equation first. Make sure your equation is balanced. You're going to need those molar ratios. So I'm going to cheat a little bit because I have the balanced reaction right here. And it's going to end up to be 2, 3, 2, 3, 2, 2. So those are our molar ratios, and you can definitely check me on that and let me know if I got that wrong. So now that we're looking at this, what can we tell about our different reactants? It's a 2 to 3 to 2 to 2 reactions, so it's kind of like an X, Y, X, X sort of thing. So we have 3 moles of O2 versus 2 moles of zinc, silicon, zinc, however you pronounce that. And it's easy to see here because it's X to X to X ratio, and this is a larger molar value, that the 2 mole ZNS is going to be our limiting reactant. Hopefully that makes sense. This isn't the case all the time. When professors present you with a limiting reactant problem, they're not going to give you really nice molar ratios to work with. Most of the time, they can give you something in grams, milliliters, anything, and you're going to have to convert it to the moles. So watch out for that when you get word problems. I guess the best first course of action is converting everything you have to moles. That way everything is on an equal plane and you can see how the molecules interact at an atomic level, or a molar level, so to speak. One way that we can kind of, if we're given we have 6.8 moles of O2 and 4.2 moles of ZNS, and we have this equation, and say the professor asks, which one's the limiting reactant out of these? A way that you can do that is make a ratio. Sometimes this helps for people if they need to look at something mathematically. If we have 6.8 moles of O2 and 4.2 moles of ZNS, we're going to divide that through to equal 1.6 mole of O2 for every mole of ZNS, and that also shows us that there's an excess of O2, that ZNS is our limiting reactant there. So hopefully, if something like this doesn't work for you, maybe putting it in a fraction or a ratio like that will help instead. And professors will give you, stuff like numbers like this, weird, scary, overwhelming numbers. The big thing is to just lay everything out plain and simple and plug and chug. We're going to move on to a particularly long example problem. 155.8 kilograms of silicon oxide reacts with 78.3 kilograms of carbon to produce 66.1 kilograms of silicon. We need to find the theoretical yield and the percent yield. We already have our actual yield here. They give it to us. I wrote down the reaction equation, and we're going to need to know some molar masses for that. So we're going to jump right in. What I'm going to do first is find how many moles of Si theoretically are produced. So I'm going to take 155.8 kilograms of SiO2. SiO2's molar mass. Oops, sorry. First, I need to convert that 1 kilogram to 1,000 grams. My bad. And now we can do 60.09 grams per 1 mole. Remember your units, but I don't have enough space, but remember your units, keep track. And this gives you 2,592.8 mole SiO2. And since Si is 1 mole part of this, we can assume a 1-to-1 ratio of SiO2 to SI, so we can say that 2,592.8 moles of SI were produced. Hopefully that makes sense. And so what we can do now is we can take the actual moles produced, which is 66.1 kilograms of SI. We can find how many moles of that theoretic or experimentally were produced. So we're going to take 1 kilogram SI, 1,000 grams SI, convert that to our molar mass, or to our moles. So 28.09 grams of SI equals 1 mole of SI, and that equals 2353.15 moles actually produced. So we have 2,592 versus 2,353. Our actual is lower than our theoretical, so we're looking good so far. And now we can find our percent efficiency by taking 2353.15 moles of SI over 2592.8 mole SiO2, or SI, my bad. Oh, my bad. Multiply that by 100%. You should get an efficiency of about 90.75%. Depending on your teacher, they might want you to round that to 90.8% yield, which is pretty darn efficient. So your experiment went pretty well. Hopefully this all makes sense. If you have any questions, please feel free to drop them below in any comments, or contact us at heychemistryblog.com or at gmail.com if that is a more efficient way for you to contact us. We are so looking forward to talking with our watchers and viewers and seeing what you guys think. Anyway, thank you, and keep your eyes peeled for video 5B coming up. Have a good night, guys.